Hi all. In the last video, we saw metric-based meta-learning for solving a few short classification problems. So in this video, we will see optimization-based meta-learning for solving a few short classification tasks. To be recollected, few short learning is about solving problems like classification problems where the data is very scarce, where very less data is available but number of classes are very large in comparison to the number of samples available for the given task. So meta learning is about having a bunch of tasks and we segregate into a bunch of training tasks and few test tasks, and the learner will be learning across the different tasks and try to generalize for the test task. So we last video we come across that how the metric based meta learning can be used for a few short learning classification problems. So again we are going to solve here for the feature classification problem using the optimization meta learning. So one of the challenges we are having a very small amount of data for a very big models having a big task is like overfitting during the optimization stage. So if we are employing a gradient-based optimization techniques like stochastic gradient, we require a large number of episodes, and that each episode and this large number of episode indirectly requires a large number of training data to travel from the initial point to the optimal point in the parameter space. But how do we going to optimize this few short learning tasks where a number of samples are very limited? So this is the idea of related to the optimization based meta learning. So there we have two stages. One is the primary task of fitting a parameter for the primary model like a classification model. The second one would be a meta learner where we try to model an optimizer. With the optimization is not like a kind of a classical one like gradient based one. The optimization itself a model which has a parameter called phi, where we try to train the phi using the data and the distribution of tasks available for the meta learning to parallelly identify the optimal parameter phi through which we uh, try to iteratively update the parameter of the primary parameter theta to finally compute the theta stars. So this is what the two stage things. One is the inner loop and the outer loop, and there are different available models which has been listed in table 6. This is the table 6, which is LSTM based meta learner, MAML, MTL, and Leo, which will be seeing one by one and in this video and the next forthcoming videos. So the stage, this is the two-stage model. This has been simplified like kind of a outer loop and inner loop model, kind of a for loop, where the inner loop will be mostly targeted upon fitting a parameter theta, and outer loop will be mostly targeted to fitting the optimal phi. That fitted model like G will be helpful to train the primary model theta for updating the primary model f. So we know that for the standard stochastic gradient descent method, where the primary parameter theta is updated through a number of episodes using this equation 15. But using this optimization meta learning, we try to have a distribution of tasks during the training time, where we try to fit the optimization model called G, where it has a parameter 5, and through which that update from the output of that G will be helpful to update the inner parameter, which is a primary parameter theta I in each episode from I is equal to 1 to number of episodes like M or N episode. The episode can be very large or very small depending upon how we have set up the architectures. So again, another paper they used an LSTM based one where we have they have taken this kind of a difference equations setup and directly try to update at each episode using the output computer from this one, where The input to this model will be the gradient of this primary model and the primary model itself, and that would help to get a g, and the g value will be output of the g value will be helpful to update the theta, and theta will be given to the f and try to compute the classification, solve the classification task. This is what primarily given in this algorithm 2, where the outer loop and the inner loop. The inner loop will be primarily focused upon the theta, and which is computed from the g. The outer loop will be primarily focused upon how to update the phi parameter using the loss function, which is computed from the inner loop. And this is what it is, computational graph for that meta learner. G will be an output of the G will be given to this F, and F output would be again a gradient, and that output of the F will be able to calculate the loss function that will be again given to the G, and the previous output of the G will be again given to this present update, and the output again will be given to the F, and this inner and outer loop will be iteratively updated using the training data, and it will be verified using the test data. This is an optimization meta learning. So this is the algorithm from the LSTM based optimization meta learning that we have mentioned here. And MAML is another one, like model agnostic meta learning. Then previously we said that we have two sets of parameters, inner loop and outer loop. And here that they doesn't try to target to do that kind of setup, but here what they try to do is they have a distribution of task, and the tasks are shared by a primary model like theta, and what it does is that optimization setup is try to find an initial prior distribution which is close enough to the optimal parameters. Once that is been find out, then that task specific update is done in a few iterative steps to identify the optimal parameters for the task at the hand. So this there are some variants of this MAML is available, which is this is tried that one metric based meta learning prototype networks is combined with MAML to obtain this setup, and this is task agnostic, where the initial setup would be too biased to try to avoid to make more generalization. So this is what the MAML, where we try to find for using a different distribution of tasks, we try to find out a good initial prior distribution. From that, we try to make a task specific update for the each and every task. And there are some limitations for the MAML, which is like instability, inflexibility, computational overhead, poor generalization, and all those things are addressed using a paper updated model called MAML++. And this is a hierarchical one, is something related to where a single parameter is not a single for all the distribution of task, a single parameter is updated, but unlike that one, it is very it doesn't accept or respect the heterogeneity. So here they cluster the task, and for each cluster they fit a separate MAML model. This context-based learning is something like they have they segregated that theta into shared data and task-specific data, and task-specific data will be updated using a specific task, and shared data will be shared, and it will be globally updated across all the tasks. So these are about the MAML. Maybe in the next video we'll see about optimization-based meta learning using this MTL and the embedded optimization. But before that, we will try to see what is model based meta learning. So far we have seen metric based meta learning, optimization based meta learning. The next video we will see about model based meta learning, all three of them, how they are utilized for the few short learning classification tasks. Thank you.